So what I do, I record every lesson so that you guys can see afterwards the lesson as well. It's probably better than the tuition center. Can everyone see the main screen of probability again?
Mm-hmm.
Okay, good. So our objectives for this lesson over the coming week are the following. We're going to look firstly at the language of probability. So my mouse is just going to hover over it, yeah? The language of probability, how we can understand probability, how we can understand some of the key words. We're going to look at the probability of single events after that, the probability of combined events after that, tree diagrams, and something called experimental probability. Most people find tree diagrams very difficult, but before we do that, we need to make sure everything else is strong. Okay, so first of all, I want you guys to write this title down, Outcomes and Events. So an event can have several outcomes. If I throw a coin, it might land on heads, it might land on tails. It won't just be one outcome. If I go outside, it might rain, it might be windy, it might snow, it might be sunny. The weather might have several or many different outcomes, okay? Because of that, probability comes in. When I go outside, if something has more than one outcome, probability gets involved. There's a chance, this word's important, chance. There's a chance that it might rain. There's a chance that it might be hot. There's a chance that it might be cloudy. So whenever we're dealing with chances and outcomes, probability is involved. Okay, so imagine I throw a 10-sided dice. What are the outcomes of throwing a 10-sided dice? So you might have 10 different possibilities. If you have 10 numbers in it, each of those numbers have a 1 out of 10 chance of occurring. So for example, if you have a 10, you don't need to copy anything, sided dice, and it's numbered 1 to 10. Each side has a number. The probability of getting the number 5 on it, what is that probability of getting a number 5 if I throw that dice? Can anyone tell me?
1 out of 10.
1 out of 10, exactly. So there's a chance of getting the number 5, there's a chance of getting the number 6, there's a chance of getting a number 7. All of them have the same probability. But what about if the dice was unfair? If one side of the dice was heavier? Imagine the dice was unfair. So now the probability of getting a 5 might be 1 out of 10, but the probability of getting a 6 might be higher. It might be 4 out of 10, because now your dice is unfair. So when things are fair, each thing will have the same probability. If a test is fair, we use this word fair. And when we say fair, we mean everything has the same probability. If something's not fair, then one thing might have a higher probability than other things. Okay? So same probability. It's just a brief note. You don't have to copy it down. Just to help you understand what's going on. Now, let's carry on. So, each outcome of an event has a probability or a chance of occurring. There is some chance of an event occurring, okay? When we write that probability down, when I wrote, for example, that a dice has a 1 out of 10 chance of landing on the number 5, we call that the probability. But you can see with probability might be involved in different situations. For example, whether it's going to rain tomorrow, whether a child born will be a boy or a girl, whether a coin will show heads or tails when it's flipped, whether a number selected at random for 1 to 100 will be even, and so on and so forth. There's many things in which we can use probability. So again, that's the basics. We measure probability on a scale from 0 to 1. Now this is important, okay? I want you guys to write the notes down that I'm going to write right now. So what we're going to do, we're going to go to notes. I'm going to write some important things down for you. So, measuring probability. Let me just write this down. Measuring probability as a number between 0 and 1. So let's write some notes. First thing, probability can be expressed as a fraction. Can be expressed as a fraction. For example, to land, or let's write this differently, to get a number 6 on a 10-sided dice will have a probability of 1/10. Converting it, you don't have to write these in detail, you can just write brief notes. I'm writing it in long form so that you can see exactly what's going on. Converting it into a decimal, so if we make 1/10 into a decimal, this thing over here, if we make that into a decimal, we get 0.1. 0.1 is between 1 and 10. So what have we done? Therefore, between 0, sorry, someone should have corrected me there. 0.1 is between 0 and 1. A bit sleepy. Therefore, we have expressed a probability, not as a fraction, but as a number. As a number between 0 and 1. Okay? So guys, do you want some time to copy that down, or can I move on? Khalid?
You can move on.
Yeah, Hannah, can I move on, Hannah?
Just a minute. I'm just writing down the last one.
No problem, take your time. Amar, you okay? This is weird, Amar, I can't hear you.
He's texting me. I don't think he can hear you.
He needs to turn his audio on. There's an audio setting, he needs to turn it on.
Yeah, I'm done.
Excellent, Hannah. So you can see, guys, how well this works. I can teach you a lesson, you can see everything. What else? Yeah, you can participate in the lesson, and good. Even if you're wearing your pajamas, you can keep the camera off. I don't have to see you guys. It's great. Okay, so we measure a probability on a scale from 0 to 1. We've just seen that what you can do, if you have a fraction, because probabilities are usually expressed as fractions, if you have a fraction, you can turn it into a decimal by dividing the top by the bottom. If we do that with the fractions and probabilities, we'll find answers between 0 and 1. So if an event is impossible, it will have a 0 out of something chance of occurring. So it will have a probability of 0. If an event is certain, if it's 100%, if there's a 5 out of 5 chance of something happening, or a 10 out of 10 chance of something happening, then the probability will be 1. If there's something between impossible and certain, then we'll have something between 0 and 1, as we've just seen. Does that make sense? Does that make sense to everybody?
Yeah.
Okay,
Yeah.
good. Welcome, Amar. Walaikum. I've recorded the lesson, so I'll send you the recording afterwards as well, so that if you've missed anything, you can look at it. Yeah. All right. So good. So we have this probability happening on a scale, okay, of between 0 and 1. You can also turn that into a percentage. Now, before we learned a few months ago how to turn a fraction into a percentage and how to turn a decimal into a percentage. If your probability comes as a fraction or a decimal, you know how to turn it into a percentage. If you don't, you can ask me after the lesson and I'll go through it with you. Okay, so let's try this. I want you to tell me the probability of getting a blue counter as a fraction, as a decimal, and as a percentage. Go for it, guys. As soon as one of you gets an answer, just say it on the thing.
Is it 3 out of 20?
3 out of 20, yeah? Basically, you count how many balls are in total. So you count the total number of possibilities first. We're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If you can see my arrow, it's counting 12, 13, 14, 15, 16, 17, 18, 19, 20. There's 20 balls in total. The ones we're interested in are the blue 3 out of 20. I can make that into a decimal. I can divide 3 by 20. And my decimal I should get is what? Can someone tell me? I should
0.3.
0.15, I believe. Are we getting that? Yeah, Amar?
Yeah.
0.15. If I turn that into a percentage, if I want to turn a decimal into a percentage, what do? I simply multiply it by which number?
100.
Excellent, Amar. So good. So I'll get 15%. Does that make sense, Hannah?
Yeah.
Okay, so I'm going to put a little rule down based on that example. Let me open up another rule. Let's start putting smooth drawn. Can you guys all see the whiteboard?
Yeah.
Excellent. So look,
Yeah.
now let's look at this. There's a special formula, yeah? The probability of something, probability, is equal to the number of what we're interested in, the outcomes that we are interested in. So in this case, we're interested in what's the chance of getting a blue? Outcomes of interest. How many we're interested in? Interest. Over the total number of outcomes. The total number of balls here were 20. So we always use this formula to understand the probability of a situation. We look at what we're interested in. In this case, the probability of getting a blue ball. But those blue balls were out of a total number of balls. And then we realized the blue were 3 and the total was 20. What we done then, you don't have to copy this, just to recap you through it. 3 divided by 20 is 0.15. And so that's between 0 and 1, as we said earlier. It's greater than 0 and it's less than 1. And then if we want to turn that into a percentage, we just times it by 100, we get 15%. So there's a 15% chance of me picking a blue ball in that situation. All right. Now, let's go back to our PowerPoint. I can imagine this part's quite easy for you right now, guys. What we're going to do, we're going to get onto the harder parts. But as you know, in these lessons, we always go for basics. Okay. So probabilities of single events. I want you guys to write this subheading down, and we can move on. So we've done the first section. We are now on the second section. Moving quite fast. Probabilities of single events. Okay. If I'm moving too fast, just let me know. I'm going to move on. So if the outcomes of an event are equally likely, then we can calculate the probability using a formula similar to the formula we just done now. You don't have to copy it. The probability of an event equals the number of successful outcomes, or what you're interested in, over the total number of possible outcomes. So if I was to throw a coin, the chance of me landing on the head side or on the tail side are equal. If I was to throw a normal dice, the chance of me landing on any 6 sides of a dice are the same. Yeah, if I was to throw a dice, the chance of me landing on the number 1 is the same as the chance of me landing on number 5, because the dice is fair, and so on and so forth. So we won't spend too much time on this. We'll go into this section. So I want you guys to think about this question and answer it using the formula you've just done now. Let's have a go. A, B, and C. You can. So Amar, what are you getting as the probability of landing on a blue sector?
1 out of 8.
1 out of 8. Excellent. Landing on a red or green sector, Khalid? Red or green?
6 out of 8 or 3 out of 4.
6 out of 8 or 3 out of 4. Excellent. When we have one or another thing, we just add the probabilities of them together. So red is 2 out of 8. Yeah. Green is 1, 2, 3, 4 out of 8. So you just add them together. Whenever you have the word or, yeah, here, you can see what my mouse is circling. You have to add them together. Not landing on a green sector. How about that one? Can someone tell me?
4 out of 8.
4 out of 8.
4 out of 8. Excellent. Do you guys know there's a formula to find the not landing one? The probability of something not happening. Does any of you know the formula for that? No one? Okay, we're going to learn that. So the probability of blue is 1 out of 8, easy. Probability of red or green is 6 out of 8. The probability of not green is 4 out of 8. And you know how to turn that into decimals. You can turn it into a percentage, easy. Right, so I'm going to write a formula down for you. And you'll see this formula again later. It's going to be very useful when you see it now. It's going to help you. Let me put this on. So new. No. Now, the probability, write this down, probability of not getting an outcome. Who can tell me the formula for this? So the probability of not getting an outcome equals 1 minus the probability of getting the outcome. That's a very important formula, and I'm going to box it just to let you know that this formula is constant. It won't change. You'll use it over and over and over again. We're going to see how that works in a second. P always stands for probability, in case you forget. It's the short way of writing it. Okay. How do we use that? Let's look. We said here, not landing on a green sector. Let's look at this carefully. Yeah. What is the probability of landing on a green sector? If I want to land on a green sector, it's going to be 1, 2, 3, 4 out of 8. If you can say 1, 2, 3, 4. But that's the probability of landing on a green sector. It's the probability of me getting the outcome. The probability of not landing on a green sector is me not getting the outcome. So if we look at the formula, the probability of me not getting the outcome is going to be probability of not green. Can you guys see what I'm writing?
Yeah.
Yeah, equals 1 minus the probability of getting it, which is the probability of getting green. So now we have 1 minus, what was the probability of getting green? 4 out of 8. If we do that as a fraction, turn that into 1 over 1, it becomes 8 minus 4 over 8. So the answer becomes 4 out of 8. We got the same thing that we calculated earlier. We calculated that the probability of not getting a green, when we looked at the diagram, we got 4 out of 8 by just looking at the diagram. When we use the formula, it gives us the answer without us having to look at the diagram. Does that make sense, guys?
Yeah.
Yeah, Hannah?
Yeah.
And Khalid?
Yeah.
Okay, so that's very important. We can go back now. We're still learning the basic rules. Let's go back to our lesson. Where is it? Here we are. Can we see the PowerPoint? Anyone can answer, just one person.
Yes.
Yeah, okay, cool. All right, so now let's start moving on. So now you guys have a question. The probability of a spinner landing on yellow is 0.2. What is the probability of not landing on yellow? Can anyone tell me?
0.8.
0.8.
Yes, 0.8, because 1 minus the probability of something happening is the probability of not happening. That's very, very easy and hopefully it makes sense. Have you seen that formula before, Omar?
No.
No? Okay, it's going to be very useful for you in school then. Okay, now, let's move on. Probabilities of combined events. Let's put this title down, guys. Start the next section. Probability of, or probabilities of combined events. So, we're back on my, what do you call it? Right out again. Probability of combined events. Combined events. Okay. So now we're going to look at some important formulas. P, the probability of A, something happening, an event happening, and the probability of B, another event happening. P, A, and B. Yeah. So let's say that it's the probability of me going outside and it raining. The probability of me looking in my pocket and finding money. The probability of me jumping out of the window and surviving. Yeah, it's the probability of two things happening together. What that means is there's a formula to write it down. It's written like this: P, A, N, B. This N part represents the word and. It's a simple way of writing it. What you have to do to work it out is you get the probability of A and you multiply it by the probability of B. We're going to learn how to use this in a bit. The second formula we're going to have, I'll let you guys write this first one down, and I'll give you the second one in a minute. The second one we're going to have is going to be called PA or B. The probability of one thing or another thing happening. That's different to the probability of one thing and another thing happening. So I look in one pocket or another one and I find £1, or a choice between two things. And you're joining two things together. Or it's either one or the other. So we write that like this in formula terms. So P, A, U, B. Okay, and U means or. That's a sign for or. You'll see this a lot in maths. We just get the probability of A and we add the probability of B to it. We don't multiply it. Whenever one thing or another happens, we add their probabilities together. Okay? Those two are very, very important formulas. You'll see them come up a lot. If there's anyone who wants me to leave this page on, say it. Otherwise, I'll move on. If someone's still copying, they can tell me. If not, in the next 5 seconds, I'll move on. 3, 4, 5. Okay. So now, let's go and do another definition. We're going to look at all of these probabilities and how to use them in a second. But first, we need another definition. The mutually exclusive event. So underneath that formula, write down a subheading, mutually exclusive events, what you can see on here. I'm going to write this definition I want you guys to copy. So you've written your title. Underneath it, we're going to write events are mutually exclusive when it is impossible for them to occur together. Impossible. So for example, if I throw a dice, let's say I throw a dice here. I throw two dice, and I add up the score and add the score. The score can only be one value. It can't be two values. It is impossible for my score to be both 3 and 4, for example, at the same time. If I throw a dice and I land two values, maybe one's the number 1, the other one's the number 2, I'll get 3. I can't have 4 at the same time. I can only have one value. So it's impossible for me to have these two things going on at the same time. Just not the way nature works. So when two events are mutually exclusive, it's impossible to have them happening at the same time. That's what the word mutually exclusive means. So we'll come back to that. Can you see my PowerPoint, Khalid? Khalid?
Yeah, I can.
Yeah, okay. So this is the example they're using here, the dice example. And they've written a long thing about it. And we don't need to go that long because it's just long. But what we can write is what's over here. Can you see that while I'm circling my mouse around? It says, when events are mutually exclusive, the probabilities of each event can be added together. I want you to write that because what we're going to do is look at tree diagrams, okay? And we're going to look at our equations and use them in a minute. So write down the title, tree diagrams, and then we're going to see how our equations work with that. So let's look at this example. You have a pack of 15 playing cards, yeah? 6 of the cards are red and the rest are black. So you can already see there's some probabilities involved. There's some red, there's some black. There's a chance of getting red or black. Write down the decimal probability of choosing a red card at random from the pack. So just think about this. You don't even have to write down. If I have this situation, what's the probability of me getting a red card as a decimal number? Think about it. I'm going to give the answer in a second. Are we getting an answer of 0.4? So what I'll say, the answer is 0.4. If any of you disagree, tell me. If not, we can carry on. So we know, and this is how we do a lesson. Sometimes I'll say an answer, and if you guys disagree, then we'll know someone got it wrong. If you don't, we can carry on, yeah? So I'm going to assume now everybody got 0.4.
How would you find it out?
So how many, remember what we said earlier, the formula, the ones you're interested in over the number in total. How many are we interested in? What are we interested in? Which color?
Red.
Yes, so the ones we're interested in is 6, divided by the total, which is?
15.
Exactly. Does that make sense?
Oh, yeah.
Yeah, remember that formula we wrote at the start of the lesson?
Yeah.
It's the number that you're interested in over the total number, yeah? Okay, so
Okay.
6 out of 15, good, 0.4. Now, you decide to pick a card at random from the pack. You replace it and then pick another. So I pick one card from the pack, yeah? So sometimes I'll make actions on the video, you can see me. I pick one card from the pack, okay? I put it back in the pack. I put this card back in and then I pick another. Okay, if you pick 2 cards, you will stay in and do your homework. If you don't, you will go out to a party. So this is the thing, your mum or dad might give you a choice. They might say, okay, you want to go out and party here, let's play a game of probability. I'm going to give you a pack of cards. Pick a card. Whatever it is, write it down. Put it back in. Pick another card. Whatever it is, write it down. If both cards you picked are red, you have to do your homework. If you don't, you can go out. So now you're worried and you're thinking, what's the probability of me picking 2 cards? Should I even get involved in this game? Is it even fair on me? I need to figure out the probability. And if it's not fair, I can argue with my parents and tell them it's not fair. Now, what we can do, we can draw a tree diagram of this situation. How does that work? Let's look at this. Your mom and dad want to pick 2 cards, and they're either going to be red or black. So the first card might be red, and the second card might be red. So you can see, you might have this situation happening. The tree diagram just maps out what could happen. Or when they pick a card, they might pick the first one as red and the second one as black. So that could happen. Or they might pick the first one as black and the second one as red. I'm tracing my mouse over it to show you what I'm thinking about. Or they might choose the first one as black and the second one as black. Does that make sense, guys? Yes.
Yes.
So, you said no, Amar?
I said yeah.
It makes sense, yeah?
Yeah.
Okay. What I want you guys to do is just basically write down the situation here. These 2 sentences. We're going to write this as an example. So underneath tree diagrams, write example. You have a pack of 15 playing cards. 6 of the cards are red and the rest are black. After you write these 2 sentences down, skip all of this in the middle and just write the situation at the bottom here, this bottom paragraph. In brief, you can write in brief notes. You can just say, make a tree diagram of the different probabilities, or you can write the situation down, which will help you to understand the tree diagram. I'll give you a few seconds to do that. Again, this PowerPoint, after every lesson, I want to email you the PowerPoint we used. I'm going to give you homeworks as well, and you'll find it on Google Classroom as well. So every lesson will come with its homeworks, will come with its PowerPoints. You can do the homework if you can. And yeah. Okay, I'm going to move on in about 10 seconds. Tell me if you want me to stay on longer. I'll count down. If you want me to stay on longer, I'll stay on longer. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, good. So now I want to figure out the answer to this problem at the bottom. I want to see if, look, what's the probability of me getting 2 red cards, 2 black cards? I draw the situation out in a tree diagram. I want you guys to copy the tree diagram as well. Okay. Next to the tree diagram, on top of every branch here, I want you to write down a probability, if you can. So what's the probability of getting a red? We said earlier, it was, if I go back, 0.4. Yeah, look, the probability of getting a red is 0.4. And it's always going to be 0.4 because you're going to get a red and put it back in. The probability of getting a second...
Does it have to be in decimal form?
Good question. Yes, keep it in decimal for now, because it's easier to work with the decimals. So Khalid, if the probability of getting a red was 0.4, what's the probability of not getting a red?
0.6.
Exactly, because the probability of not getting something is 1 minus the probability of getting it. And when you don't get a red, what do you get? Black. So the probability of getting a black is 0.6. So here if we write it, 0.4, 0.6, 0.4, 0.6, 0.4, 0.6. We've now got a very good diagram of what's going on, but we still haven't got an answer. Because what you might have is 2 reds, beautiful, or red and a black, not too beautiful. Black and a black, homework, worst. Or a black and a red, again, not too bad, but still, you don't want a black and a red, you want 2 reds. So what's the probability of me getting a red and a red? A red first one and a red for the second one. Can anyone tell me?
Can you repeat that?
Yes. So I'm asking, what's the probability of me getting a red on my first pick and on my second pick? Because we're picking 2 cards. How do
0.8.
You said 0.8, yeah? Okay. Do you guys remember a formula we wrote down a few minutes ago?
Oh yeah.
The probability of A and B. If you're the probability of getting something and another thing, what do? You simply multiply them. Yeah, you times them. Yeah. So we wrote that in our notes a few minutes ago. The probability of getting A and B. Let me just bring you back to the notes. I think if they're still there.
0.24.
Yes, we're coming to it. So look, let's just look at. I'm just going to show you this quickly. Share my screen. Share this. You can see P, A, and B. The probability of something happening and another thing happening, you write it like this, is just you multiply both of them together. So as Khalid said, is 0.4 times 0.4. We should be getting, let's check, 0.4 times 0.4. We get 0.16. Someone to 0.24, that wouldn't be correct.
It was 0.6.
0.16, yeah?
Wasn't it a red and a black?
Red and red. We're going to do red and red first, and we can do red and black in a minute, yeah? But as long as you understand the method, that's what's important, yeah? So red and red is 0.4 times 0.4, we get 0.16. Red and black is going to be 0.4 times 0.6, so that becomes 0.24. Then this one, black and red, 0.6 times 0.4. And this one, black and black. You see what's going on, guys?
Yeah.
Yeah? So are the parents playing a fair game here? Not really.
No.
No, because the probability of getting a black and a black is actually higher than the probability of getting a red and a red. Does that make sense, guys? Oh. Yeah,
Yeah.
Mar? Good. So this is how we do tree diagrams. In tree diagrams, we look at a situation and we turn it into a tree, as you can see here. Next to each situation, we write the probability of it happening. Because we do that, we can do more complicated things and then look at the probability of two things happening, combined events, which we wrote a title down for earlier. Combined events. When events are combined, there's formulas you can use. The probability of A and the probability of B. There's another formula as well, which we wrote down. The probability of A or B, which we'll come to next. So, we've written those probabilities up. What do they all add up to? If I add them all up, they should add up to 1. Because the probability of every situation happening adds up to 1. We said that at the start of the lesson. What are the chances of going to the party? So, you can only go to the party if you get, let's see. Oh, sorry, you can go to the party if you get 2 black, if you don't pick 2 reds. Yeah, as Colin said, so I didn't read that properly. You can only go to the party if you don't pick 2 reds. Because it says here, if you pick 2 red cards, you'll stay in and do your homework. So, what's the probability of me going to the party? I can only go to the party if which situations happen? If these 3 happen. The second one, third one, and fourth one. Anytime I don't pick 2 reds, I can go to the party. So, it's the same thing. You guys have understood the method. Because I read the question wrong, instead of looking at the probability of 2 reds, we look at others. But the question's not important because you understand how to do it now. So what's the probability of, what's the chance of me in this game going to the party? Well, the chance of me not going to the party is 0.16. Yeah, if I get 2 reds, it's 0.16. Which formula could I use here? Can someone tell me? We learned it earlier.
Probability of A plus
Is it
probability of
1 minus?
Yeah, you can do it 3 ways. You can do it 3 ways. Both of you said something good. Amar was hinting that you add these up. You add the ones of the probability. You add the probabilities up of going to the party. Yeah, so 0.36, 0.24, 0.24. You add them all up. Yes, correct. Khalid was saying, no, look, remember earlier, if you do 1 minus the probability of something not happening, 1 minus the probability of something happening, you get the opposite. So let me explain that in a better way. Let me just go to the slide. So if I open up a new screen, okay, the probability of something.
So can you do it both ways?
You can do it both ways.
Oh.
Yeah, the probability of something happening is 1 minus the probability of it not happening. So the probability of getting red, 2 reds, is 1 minus the probability of getting no reds. Does that make sense? Everyone okay with that? Yeah? What we could do in that question is we said that the probability of getting 2 reds was 0.16. So the probability of not getting 2 reds, of going to the party, is 1 minus 0.16. And we'll get an answer. Does that make sense, guys?
Yeah.
Yeah.
Yeah, good. Hannah? Hannah, it makes sense because Hannah's using the new method, which is good. The staying silent method. I like it. Good, good, good. Well done. So, is there any confusion there, guys? No confusion? Good. So, let's look at this. Probability without replacement. If you guys write this down, we're going to practice much more of these later, so don't worry. We're just going through examples. Probability without replacement. Write the title down. We're going to write the exam. We're not going to write the example down. Let's look at this question together now. It is 7 a.m. The light bulb has gone. You're in a rush. So because you're in a rush, you're going to rush to put clothes on. There are 20 socks in a drawer. 14 of them are blue and the rest are green. What is the probability of randomly picking a blue sock out of the drawer? Tell me, Khalid.
14 out of 20.
So yes, good. Because you've had the one you're interested in out of the total, which you've understood. 14 out of 20. 7 out of 10, if we simplify it. 0.7 if we turn it into a decimal. Okay. So you pick out 2 socks, one after the other, in the hope of getting a matching pair. So what these 14 and blue are, they're single socks, yeah? They're single socks, as they've just told us. I thought they were a pair, but they're single socks. So you've got 14 single socks that are blue and 6 single socks that are green. When you go into your drawer, you're picking 2 out. So you might pick a blue one and a green one. You might pick a blue one and a blue one. You might pick a green one and a blue one. You might pick a green and a green. So if you pick 2 socks out, one after the other, and you wear them, and you go to school, what's the probability of you having a matching pair? That's the question. Let's look at that in a second with the diagram. So all I want you guys to do first is write down the situation in rough. You can write 20 socks in a drawer, 14 blue, 6 green, and what is the probability of getting a matching pair? So quickly, just write a quick question down. And after this, we can have a break if you want. We'll carry on if you don't. Let's see. So I'm going to move on if you guys are done in 5 seconds. If not, let me know and I'll leave it on. Okay, you guys are done. Good. Now, let's look at the tree diagram. My first sock and my second sock, there's 2 things that I'm going to do. Your tree diagram maps out what you're going to do. Yeah. My first sock might be blue, my second sock might be blue. I'll be happy. First sock might be blue, second might be green. Not so happy. First might be green, second blue. Problem. First green, second green, happy. Now, let's write down our probabilities. In this case, when I pull out my blue sock, I'm not going to put it back in. It's dark. As soon as I pull out my blue sock, I'm going to wear it. And as soon as I pull out another sock, I'm going to wear it. So in the previous example with the cards, once we picked a card, we put it back in. In this one, once we take out a sock, we don't put it back in. There's no replacement, we say. So initially, my probability of getting a blue sock is 7 out of 10, which means that my probability of getting a green sock is 3 out of 10. Does that make sense? It does, because you guys are not replying. It means it makes sense. Good. But now look at this second part. What's the probability of me getting a second blue socks? 6 out of 9 or sock. Why is that? Why is that? Why is it not 6 out of 10?
Because you took out a sock, so there's less.
Yes, so the total number of socks is less. Now I took out a sock, yeah. The first one was blue, so I now have six blues left. But because I have 6 blues left, on the second time, I'm going to take it out of 9 socks. So I'm only going to have 6 out of 9 as my probability. Does that make sense, guys? Well, actually, don't tell me yet. I'm going to go for a few more, and then we'll see if it makes sense. So my first sock might be 7 out of 10 blue. Now if I've taken 1 sock out, I've got 9 left in total. So my second one will be 3 out of 9 for green. If I pick a green one on the first go, 3 out of 10. On the second go, I'm going to have 9 to take the socks out of again. So my second go, I might have 7 out of 9 blue and 2 out of 9 green. So before I carry on, is there anyone who doesn't understand that and needs to explain? Because I can explain it in a second if you want. Everyone's got that. Good. So this is called probability without replacement. Yeah, you're not replacing it. You're taking something out and keeping it out. If you take something out, then if you look at the PowerPoint, your probability has to reflect that. Your probability has to show that you took something out. You haven't got the same number in total anymore, so you've taken one away. Does that make sense, Amar?
Yeah.
Excellent. So now, the probabilities. If I want to get a blue and a blue, one and the other, what do? I simply multiply them. I personally turn it into a decimal. You can multiply the fraction as well. Blue and green, multiply them. Green and blue, multiply them. And green, multiply them. And you get your probabilities. So it's that easy. On a tree diagram, you've just got to write the possibilities down. You've got to write the probabilities down. And then it's done. Okay. So now, next one. Right. What do the probabilities add up to? You guys should know now. They always add up in total to 1. What is the probability of getting 2 socks of the same color? Okay, now let's look at this. What is the probability of getting 2 socks of the same color? How do you do it?
Would you do blue and blue as green and green? Or
Yes, you add them. Why don't you multiply them in this case?
because we're doing blue or green?
Yes, exactly. If you have the probability of one thing or another, you add them. So let me talk about that again. So we're looking at the probability of getting 2 socks of the same color. If you look at my PowerPoint, I'm circling blue and blue now. That's 2 socks of the same color, probability of 7 over 15. And green, probability 1 over 15. But they are on different branches. Blue and blue is on this top branch over here. Green and green is on the bottom branch over here. Whenever you have 2 things on different branches and you want to see the probability of them happening, you add them together. That's a very important rule. Whenever you're looking on a branch, you multiply them. So what does that mean? If I wanted blue and blue, 7 over 10 times 6 over 9. If I wanted the possibility of having 2 blues or 2 greens, you add the probability of this part to that part. Or means you add them. Anytime you're on 2 different branches, you have or. Anytime you're on the same branch, you have and. Meaning, anytime you're on the same branch, you multiply. Anytime you're looking at 2 different branches and trying to bring them together, you add. Does that make sense, everyone? Yes, I believe. So what is the probability of getting 2 socks that don't match? So we're looking at 2 different branches. This one and that one. Meaning we add this to that. Very easy. And done. Now I'm going to ask you guys, do you want a 5-minute breather? Tell me.
Yes.
Yeah, 5. Khalid, 5 or not?
Okay.
Yeah, how about you, Hannah? 5-minute breather?
Yeah.
Okay, keep your
Yes.
computers on. Don't log off or anything because we're going to come back in 5 minutes to the same thing. It's 5:05 now. We'll be back at roughly 5:10. Okay. So what I want you guys to do is draw up a tree diagram for the following. Yeah. 2 kings in a row or 1 king. You know the probability of getting a king is 4 out of 52. Because you know that, you can do the rest. Have a go at drawing a tree diagram for that situation. Hannah, do you feel these lessons are useful?
Yeah.
Okay, good. Do you think they're as good as the center or better? Good enough, Hannah?
It's all right. Yeah.
Yeah, good. The good thing about this, everything's recorded. So after the lesson, you can watch it again as many times as you want. And I can have breakfast while teaching you guys. So once any of you are done with the diagram, please let me know. Just shout it out. And then we'll move on.
I'm done.
Done? Okay. So if you're done, if you're doing it still, no worries, you can do it. I'm going to go through the answer as you're doing it. So when we write our probability trees, as we get used to it, it'll become easier and easier to understand how to write a tree down. In this case, we have a situation of getting either 2 kings or no kings, or one king and another king, or one king and one not king. So we do the situation as this: king, not king. The second one, king, not king. If you notice on the tree diagram, every tree is a copy paste of the first tree. Yeah, as long as you get your first tree right, every other tree is going to look like that usually. So the probability of me getting a king is 4 out of 52. The probability of me not getting a king is going to be 48 out of 52, or 1 out of 13, and then 12 out of 13. The probability of me getting a second king now, because I've removed one from the deck, is 3 out of 51. And not a king is 48 out of 51. And so on and so forth. I want to see if you guys are getting the right. Has anyone not understood that first? So everyone's understood that. Good. So when you work it out, the probability of getting 2 kings is you multiply, because you're going along the branch. As we know, when you go along the branch, you multiply. You get this, you multiply them together, get a big number, simplify it. King and not king. And notice how they write probabilities. They write the word P and a bracket and the things you're interested in. Yeah, king and king, or king and not king. Multiply them out, get that. And we carry on, and we carry on. So tree diagrams are very simple. You have your probabilities, and you just multiply across the branch. When you go between branches, you add, which we're going to look at later. So what do the probabilities add up to? You can see the pattern, 1. What is the probability of getting only 1 king? Only 1 king is this situation here and that situation there. They are on different branches. Because they are on different branches, what do you do? As Khalid said earlier, you add them. And we get our answer. So I want you to write this down. Remember, in tree diagrams, you multiply along the branches, but add when selecting outcomes from different branches. They made it look complicated, but after add, just say across the branches. With that rule, you can do any tree diagram, hopefully. So let's do a harder problem. In a class of 30, 24 people have mobile phones. 18 are connected to the internet and 14 have both. I want you to write this down and first make a Venn diagram. On your Venn diagram, you should be getting something like that. Is everyone okay with that? Okay. Now the questions are, oopsie daisy, what is the probability of selecting a people at random who has only a mobile phone, or the internet, but not both, neither a mobile phone and or the internet? So I want you guys to think about the answers to these 4 questions. I'm going to give you 3 or 4 minutes. We're going to go through it. What is the probability of a student only having a mobile phone? Only a phone.
Is it 10 out of 30?
10 out of 30 or 1 out of 3? Exactly, because the mobile phone owners are only 10 out of a total of 30. If you look at the total, if you just look at the question, it tells you there's 30 in total. So 10 of the 30 are mobile phone owners. Everyone's okay with that, I guess. If not, just tell me. Okay. A mobile phone or the internet, but not both. One or the other. What do we do here? Let me ask you, Hannah.
Do you add the mobile phones and the internet together and that be over 30?
Very, very, very good. So 10 over 30 plus 4 over 30. Yeah? Does that make sense, Amar?
Yeah.
Okay. Sometimes on the board, they've answered it wrong, so don't worry about that. Neither mobile phone nor internet. Can anyone tell me?
Would you add 10, 14 and 4, then do 30 to take away that?
Yes. Well, not even take away that. If you do 10, 14 and 4, you realize there's 28. 10 people on mobile phones, 14 people on both, and 4 people on internet, yeah? If you add them together, it means 28 people altogether have everything, yeah? But that means there's 2 left out of 30 that have nothing. So 2 out of 30 is 1 out of 15. Does that make sense?
Yeah.
Okay. Everyone okay with that? Okay, so the or rule. The word or, we looked at it earlier, often indicates that probabilities need to be added together, one thing or another. So we add them. We usually use it when events are mutually exclusive, when they can't happen at the same time. Now this is interesting. We looked at the word mutually exclusive about 20 minutes ago, and I said we'd return to it, and now we're returning to it. So when two events can't happen, when it's impossible for two events to happen at the same time, we can add them together. Let's look at an example in our tree diagram. It's not possible for me to have the situation in the top branch and the bottom branch at the same time. I can't have two kings and two not kings at the same time. But I might have chosen two kings, or I might have chosen two not kings. Because I can have one or the other, I can add them together. Whenever you have probabilities you can add together, they're usually going to be mutually. Okay, good. So that we're looking deeper at the reasons why or exists. Now, so P, A, or B. The AND rule. The AND rule is when two things can be multiplied because one thing and the other have to happen. The probability of picking two kings. I have to pick one king and another king. And so I can multiply them. So we use this where the events are independent, which means they can happen independently of each other, but they're not mutually exclusive. If I pick one king and I pick another king, they're two separate things. But I can have them happening one after the other. Right? So I can use multiplication where there's independent events, and I can use addition where there's mutually exclusive events. I hope that makes sense. Now, we're going to look at the last bit, which is experimental probability. After we do that, we can look at the exam questions and really go into detail with those. So let's write down the title, experimental probability. Now, this is about expecting things. You're predicting things. Like people play the lottery, they predict that these numbers might come up this week. What's the chance of this happening? How much can I expect to win? So if you flipped a coin 50 times, how many times do you expect to get ahead? What do you think, Amar? If you flipped a coin 50 times, how many times do you think you'll get ahead?
25.
25, yeah, roughly, maybe. It's correct. I'd say the same thing because the chance of getting a head or a tail is 1/2. There's two things you can have, a head or a tail. The chance of getting a head is a half.
No, actually, it could be any because.
It could be, but what's likely is basically half, yeah? So because when you flip a coin, you have a probability of a half of getting a head and a half of getting a tail. There's two sides to a coin. The probability of getting a head is 1/2, yeah? So if you flip it 50 times, half of it should be heads, roughly, you'd expect. Yeah, just looking at the probabilities. But let's look at that in more detail. I'm just chucking a dice. You don't have to copy this down. The probability of getting any number on a dice, P of any number, is simply going to be 1/6. If I want to get the number, if I floor a dice and I want to see the number 1, there's a 1 out of 6 chance of getting that because the dice has 6 sides. If I want to see the number 5, for example, there's also a 1 out of 6 chance of seeing that. If I want to see the number 6, there's a 1 out of 6 chance of seeing that, and so on and so forth. Yeah. Now, if I throw the dice 60 times, then how many times am I going to see the number 5? Because the chances of getting a number 5 is 1 out of 6, I can do 1/6 times 60. I'll get an answer of 10. So roughly I'm expecting to see the number 6 10 times, right? But that might not happen in reality. Other things might happen. As you know, it's not an exact science. Probability gives you an estimate, but it doesn't give you exact numbers. It gives you a rough idea of what you should get. Okay, so it's like when you go to a boxing match. If someone punches you this hard, I can expect to get knocked out probably. It might not happen, but there's a high probability that it will. So let's go back to our slide. When I throw a dice 60 times, I will get 10 sixes because the probability of getting a 6 is 1/6, says Zara. Roughly accurate. Okay, but then Monica throws the dice 60 times and she gets results like this. She gets a 6, maybe 11 times. Look, it's close to 10. It's not exactly 10. She gets a 4, 14 times, which is not too far from 10. A 3, 8 times, which is not too bad. 2, exactly 10 times. 1, 12 times. Most of the answers are close to the expected probability. but on occasion you'll get one answer that's very far from it. So what the expected probability does, it gives you a good idea of what's going to happen most of the time, where the answer is roughly going to be. But it can't account for those random things as well. Yeah. So it's got some benefits where you get a rough idea, but you don't get an exact idea. So Zara is wrong, but she's got a rough idea of what's going on. So if you look at Monica's results and we turn them into fractions, what you can do is relative fruit. We're going to look at this now. So if you write this down, so I'm going to write something down for you, some notes, because I haven't done it in the PowerPoint. Let me, 1, 2, 3, 4. Is someone missing? Someone's missing from the lesson. No, everyone's here. Okay. And you. So write this down. Expected probability. Just write a formula down for now, because it's just all about formulas really. This is probability. So to calculate, the formula is expected probability equals the probability of an outcome. So to get a 6 is 1 out of 6, for example, times the total number of events. The total number of events. So if I throw a dice 60 times, that'll be my total number. If the chance of getting a 6 is 1 out of 6, that'll be my probability. 1 over 6 times 60 equals 10, which will become my expected. All you guys need right now is this formula over here. Okay, so once you get that down, we'll move on. Okay, so now that you've probably got that down, there's going to be another formula we look at, but this is your first one. I want you to get the next bit of notes down as well, which is relative frequency. Relative frequency. We're nearly coming to the end of probability. We've only got 6 slides left, and then we're going to do a lot of exam practice later. 1 second, so you can't see my screen. Can you see my screen now, Khalid?
No, we can't.
You can't? Okay.
Mm.
I've shared my PowerPoint with you. Can you see it now, Mar?
Yeah.
Okay, good. So I want you guys to copy the title down, relative frequency. And here, what we're going to do, because it's important to have it in note form, I don't like writing too many notes because sometimes it's a waste of time, but today this is important. I wanted to introduce this table, but not with how they've introduced it. You can write, Monica throws a dice 6 times, and these are her results. Sorry, Monica throws a dice 60 times, and these are her results. So Monica throws a dice 60 times, and these are her results. We're just doing a note-taking activity here. Monica throws a dice 60 times, and these are her results. I want you to copy the table and copy the fractions in the table, because we're going to take some notes on it. These fractions are called the relative frequencies. I need you to write that down as well. It's very important. So the frequency related to something, the amount of times something happens related to something. So the number 1, related to that, 12 times out of 60 it can happen. Number 2, if I want to get 2 on my dice, related to that, 12 times out of 60 I can get number 2. So this is relative to that. They're both related to each other. This is the amount of times I get a number 2. This is my number 2. So it's a relative frequency. This is a frequency, or the number of times something happens relative to a particular value. Relative frequencies can also be called experimental probabilities. In an exam, they'll ask you, what's the experimental probability of getting a number 2? Now, if you don't know what that means, you won't realize the answer is so easy. You just say 12 over 60. Yeah, that's what the answer is. The experimental probabilities for a dice are not always 1 over 6. The probability of getting a 1 should be 1 over 6. It's not exactly going to be 1 over 6 when you break this fraction down. 2 should be 1 over 6. Again, not exactly 1 over 6. 3 should be 1 over 6 on a dice, but when in real life, when you do it, you find the real results are a bit less than 1 over 6. So you can see the experimental probabilities are not always the same as the real probability. And the last bit you don't need to copy. So these 3 things you need to copy down.
What does the relative frequency like actually mean? Like, what does it mean?
So it's a good question. The frequency of doing something is how many times you do it. So for example, if I eat 4 times a day, my frequency of eating on Monday is 4. My frequency of eating on Tuesday I might eat 6 times a day. So my frequency of eating on Tuesday is 6. Relative frequency is where you link the frequency of something to what you're doing. So my relative frequency for Monday is 4, linked to Monday. For Tuesday is 6, it's linked to Tuesday. So the frequency is something happening, the probability of something actually happening, linked to what you're talking about. It's relative to that. Does that make sense, Amar?
Yeah.
Yeah, good. You want me to write it down, or do you get it?
I get it.
Okay. So I'm going to give you guys another 15 to 20 seconds to copy this. If you need more time, then I'll give you more time. But if no one says they need more time, I'm going to move on in 15 seconds. We're going to do some questions on probability. Beautiful. Found it. Let's make some exam style questions up. Okay. So now when you see these questions, don't get scared because they're not difficult questions. They're very easy, in fact. It's just that we need to go over them. And when you go over questions sometimes, things look difficult and they're not in reality. So let me just make this a bit smaller. 1 second, let me load this up over here. I'll send you these questions online as well. But for now, what we'll do them as a class. So this is an actual exam question. These are actual exam questions that have popped up from GCSE at A level. Oh, sorry, GCSE papers. Let me log on to the question for you so you can see it. Okay. Can you guys see the exam paper on the left-hand side? Communication, guys. Can someone tell me? We can see this. Yeah, excellent.
Yeah.
So I want you guys to write down the title, which is Probability Test A. Questions. We're going to do some questions together. And we're going to look at the answers. The answers are on the screen, but I'm going to take them off for a second because we want to make sure we get it. Make this a bit bigger. Okay. Now, after you've written down the title, I want you to try these questions. So now when you look at, I'm going to email you these questions. So when you look at your email, you'll have a question paper. In your book, you'll have the answer. So student, start with question number 1. Let's have a few minutes to do that. So why is this table incorrect, guys?
Is it because?
It doesn't add up to 1.
Yeah.
Yes, it adds up to more than 1. And so probabilities of anything should always add up to 1. Does that make sense, guys? Exactly what we learned in lesson, yeah? Han, does it make sense?
Yeah.
Okay, good. The first 2 figures are right, but the one for cauliflower cheese is wrong. What should it be? So you guys can work that out.
0.25.
Yes, you add the ones for pizza and chicken pie, which is making me hungry, and you subtract it from 1 to get the remainder. Does that make sense, guys?
Yeah.
Yeah, Hannah?
Yep.
Yep, good. Okay. So with these questions, I'm going to ask you every question if you get it. It's good. Now, this is going to be an interesting one. 32 students chose pizza. How many students chose chicken pie? Hmm. I'm going to give you guys a second to try this one out. This is where probability connects to other things.
Which one?
Number or C.
Okay.
Yeah. If 32 students chose pizza, how many chose chicken pie? It's about ratios.
I'm not good at ratios.
No problem. I think you missed the lesson in ratios, Amal. We done it. But I think you weren't there that week. But I'll teach you it again at some point, okay? All right, don't worry. Let me just see how I'm gonna show you guys through this question how to do it in a minute as well. I want to see what Khalid and Hannah are getting for this. Any idea, Hannah?
I'm still doing it.
Okay, take your time. Khalid, any idea?
I think I got an answer.
Okay, I'm gonna give you another. Let's say I'll give you guys another minute. Okay, let me see. I'm gonna show you the answer, but I'm not gonna tell you how to do it yet. I'm just gonna see if you guys can get the answer. So C 32. Yeah, 27 should be your answer.
I didn't get that.
You didn't get that? No problem. So have another go while we wait for Hannah for a minute. Let's give you guys another minute and then we'll look at it.
I have no idea.
No idea? No problem. No problem. We're gonna learn it. Hannah, ready for an answer?
I'm a bit confused.
No problem. It's a confusing one. It's fine. So I want you guys to look at the mark scheme here first, and then I want to teach you how to do it, yeah? This one. There's many ways you can do this, but I'm going to show you this one. And I'm going to teach you my way in a second. Try and think about that, all of you, for about a minute at least. I just want you to think about what they've done there. Okay. Now I'm going to take you through it. Let me load up my, oopsie daisy. Load up my page, whiteboard. Okay. Get a new screen. Okay. So they said, if you look at the probability of pizza, it was 0.4, right? Do you guys agree with that?
Yeah.
Yeah? Okay.
Yeah.
Now, 0.4, if we turn that into a percentage, what do we get? 0.4, 40% of students had pizza. Does that make sense?
Yeah.
Okay. Now, how many students were there? 40% of students equals 32 students. So that's 40% out of 100. Yeah. So there's if you had 100% and you had 40%. To go from 40 to 100, what do you have to multiply it by? 2.5. Yeah. So if you had 30, so 40% gives you 32 students. So what do I have to do to 32 to get to the number of students in 100% of people? 32
Times
times
it by
2.5.
2.5.
We get 64, 78 students altogether. Sorry? So I thought someone said something. So if you times this by 2.5, 32 times 2 is 64. And then the 0.5 will give you, it should add up to 80 students altogether. 80 students in total. Now, before we carry on, does this part make sense, everyone? How I worked
Yeah.
out, yeah? Does that make sense, Hannah?
Yeah.
Amar, makes sense? Hannah?
Yep.
Yeah? So if I have 80 students in total, 80 students in total, and Khalid told us that 0.25 have chicken pie. You can do two things now. What's 0.25 of 80? You times that by that, you're going to get 27. Or you could say 0.25 is 25% of students. What's 25% of 80? 25 over 100 times 80 over 1. We're going to get 27. Do you guys see how that works? In fact, what I'm going to do, we're going to go back to the question and you're going to re-answer it without looking at my notes. So let's go back to our screen. Look at this question and now try. Okay. And if you still don't get it, don't worry, we're going to go through it again, a different way. How about you, Hannah?
I got 27.
Good, that's correct, yeah?